Morning. This is joint work I've done with Greg Kuhlmann, who is another graduate student at UT, and Peter Stone, our advisor. This is way too loud. So this is a slide that I don't expect you to absorb at all. This shows some of the quantitative results from our paper, which I'm going to touch on at the end of the talk, but instead I'm going to spend the majority of this talk talking about transfer. Transfer learning, what it is, why it's important, and why it's important for AGI. I think most people will agree that transfer learning is essential for AGI. If you disagree, I'd be interested to hear why. The problem is lots of current machine learning techniques have a number of shortcomings. They're often just applied to simple tasks, whereas in AGI we're interested in very complex tasks. They're often data inefficient. So if we're trying to decide if an agent is intelligent and it learns very slowly compared to humans, we may not think it's intelligent. And lastly, current machine learning algorithms need a lot of human knowledge, and we'd like to minimize that. One approach to trying to solve these problems, the one I'm advocating today, is the idea of transfer learning. So transfer learning is related to lifelong learning or multitask learning. I can talk more about that later if you're interested. But the general idea is that instead of just focusing on one task at a time, I want to learn how to generalize across tasks, across problems. And if I can do this effectively, then I can learn faster. I could probably learn how to solve harder problems. I can learn with less human input, and I would argue it's actually a prerequisite for AGI. So if you have some agent that you're claiming is intelligent, and you throw it at this new problem, throw it at this new task, and it can't robustly reuse things that it's learned, you're probably not going to think it's too intelligent. So on the left here, I've got a diagram of soccer, simulated soccer, which is one of the domains I work with, and I'm going to use it to illustrate two different transfer learning scenarios. The first one is, think of I'm a human and I want to solve some difficult task. So I've got a bunch of simulated agents and I want them to learn to play soccer. Well, instead of having them tackle the difficult 11 versus 11 soccer, maybe I can have them learn this simpler game first. And maybe I could construct a sequence of tasks so that they could learn the sequence faster than if they trained directly on the final task. And our work has shown this is possible. A second scenario, which is more relevant for AGI, is that of autonomous transfer. So the idea is I've got some agent that's exploring the world and is coming across tasks, learning how to do different things, and now it's got a new task. And now it needs to figure out how to effectively use knowledge from a past task to learn its current task. Okay, so what do I mean by a task? In my work, I'm mostly dealing with reinforcement learning, which is a general framework, as we saw in the last talk, for an agent interacting with an environment. And you could think of this, so for instance, you could have an agent that's learning how to play backgammon, say. So Jerry Tesoro's work on TD Gammon. Or you could think of incorporating this reinforcement learning as a module inside of SOAR, like John Laird has done. But whether this is a standalone RL agent or it's part of a component, in transfer, we're saying we have some source task. And then we want to show how to use that to speed up some target task. So these are, in reinforcement learning, these are different MDPs. So they're somehow related, but different. So going back to the soccer example, you could have different numbers of agents in these two tasks. So they're both soccer, but because there's different numbers of agents, you have to describe the state differently, you have different numbers of actions. Now what is transfer good for? Here's an example learning curve in reinforcement learning. So along the x-axis we have training time, which has to do with data used. The y-axis is performance. So here you can see over time these agents are learning to perform better. This is learning without transfer. Here's, now in green, is a transfer learning curve. And you can see some of the possible benefits. First is jump start. When you're in this new task, you're immediately able to perform better. You might have some asymptotic performance benefit, so that the ultimate policy, the ultimate performance you achieve, is improved by transfer. You could also think about the total reward accumulated, that kind of thing. These are possible benefits of transfer. And I should mention that these are some results that we have from the simulated soccer domain. The next question is, well, what can I transfer? And the work that my group has done, along with others, has pretty much said there's a whole bunch of things you can try to transfer, and it actually works. So for those of you familiar with reinforcement learning, these first 3 bullet points are fairly low-level, task-specific details that you can transfer between tasks and improve learning. You could also think about transferring higher-level knowledge, so rules or advice, learning rates, things like that. In my past work, I've managed to transfer the different items that I just circled there. But the take-home message is there's lots of different things you can transfer between reinforcement learning agents. How can you transfer? Well, that's going back to which scenario you're in. So if there's a human in the loop, so I want to learn the full 11 versus 11 soccer task, then I could, as a human, construct a sequence of tasks of increasing difficulty and let the agent know how they're related so that the agent can transfer knowledge effectively. For AGI, we're more concerned with a fully autonomous situation, and I should mention this has not been achieved yet, but there's a number of groups that are working towards this problem. So here you have to learn, I've got a new task, now I need to decide, is this new thing related to something I've learned before? Because if it's not, transferring could actually be exactly the wrong thing to do. Then the second question is, okay, I found a task that's similar to my current task, now how do I figure out if, now that I know that the tasks are related, how are they related? For instance, how are actions in one task similar to another one? How are state variables or features in one task similar to another task? So this is actually my last slide. And the paper that's in the AGI proceedings has to do with how you would select the source task for some given target task. And we show that it's possible to transfer search heuristic. Now, the particular game that we use in this paper is Mummy Maze here, and it's one of the games in the general game playing domain. If you're not familiar with that, this is a competition that's held yearly, which is particularly appropriate for AGI. So the idea is that you have an agent, a program, which can play a game that it's never seen before. So different teams field their agents, they come to the table, and then they're given a game description. And they very quickly need to come up with a way for playing against other agents, which have never seen this game before. So a good potential application for many of you. So hopefully, and very briefly, I've given you an idea of what transfer learning is about, why it might be useful for AGI. So if you're interested, please look at the paper. I'd be happy to suggest more references later offline. Another option is if your work is somehow related to this, please consider submitting to our AAAI workshop. The deadline's coming up next month. Or if you're going to AAAI and you're interested in learning more about current techniques in transfer learning, please consider stopping by. Thank you.